conscious of a mixed audience, and I'm sure throughout this talk, somewhere along the line, I'm going to be teaching grandmothers to suck eggs. So I thought I'd Google and see if I could find a cartoon that explained what that expression meant. And this is the only cartoon I could find on Google, and I still don't know what the expression means in reality because I've never sucked an egg in my life. So I've been asked to talk about my journey going from how to work out how to get from a CT scan to a physical model of a broken bone. I'm an orthopaedic surgeon in northeast London. My disclaimer up front is that I've done this work with the help of Ultimaker, who gave me, without any strings attached, literally or metaphorically, a printer to help me do what I wanted to do. There's no contractual arrangement, I have no written understanding, but I still have the printer. So I'm an orthopedic surgeon, so what do? Well, a lot of what I do is fix broken bones. So for the uninitiated, this is a side view of someone's elbow, and everyone can see that it's not quite connected as it should be. And with the help of a lot of metal and screws, you can connect it all back together again. You can do this on a smaller scale. So this is just a finger. If you look at your finger and think about the size of it, that fracture is pretty small. And we have very small things to fix it. The screws are 1.3 diameter, so we use a drill that's 1 millimeter diameter. So a little more delicate than what a lot of people think about orthopedics, I guess. So in 2011, I was listening to the wireless, as they say, and an orthopedic registrar, a trainee surgeon in Scotland, talked about how he was using some open source software to print out models of bones. He at the time was using a Mac, which seems stupid, and some software which was free at the time, but he still wasn't printing it out himself. And I actually got in contact with him, and at the time he said, oh, you can't do it yourself, the printers cost £20,000, it's not realistic. I did look at the kind of alternatives. There still is online and outside 3D systems, incredibly expensive. You have to kind of pay for the time you use online. You can buy software. I was talking to a company in America last week, and it's only a couple of $1,000s a year. There's a company in London who are about the cheapest. They'll take a CD of the CT, and they'll send you back a model, but it takes them a couple of weeks, which is no good if you've got a broken bone that you want to fix tomorrow. Materialise, who are outside, are a little more expensive, and it's not really their thing to produce fresh and acute models. So my goal was to do something that was affordable for either an individual or a department, hopefully using free software, using a desktop printer, however you like to describe it, so low running costs. And I wanted something where I could see a patient today and have a model in my hand ready to operate on them tomorrow. Hopefully it would run without buying a new computer, and hopefully be plug and play. So in 2013, there was a 3D print show in London, which was at the Business Centre in Islington. I don't know if anyone was there, but compared to this, it was like a back room with about 5 companies and a few 3D printers. But it was quite a magical experience, and I started talking to Ultimaker and said I wanted to do this challenge, and they said, here, have a printer, see what you can do. So then, having got a printer, I needed to find some open source software. Before we go any further, for the uninitiated, I just need to clarify a bit of terminology. DICOM, DCM, so this is the file format that X-rays come in. It's a bit like JPEG for your photographs. All radiology and medicine are DICOM files. I'm sure you all know an STL file is the file that is the 3D virtual image of your thing, be it a bone or anything else. And G-code is the code that you need to use to control your machine to make your 3D model, be it additive or reductive, so either a mill or a printer. In additive, 3D printing is really slang for additive manufacture, and FFF is fused filament fabrication, which is what these printers like Ultimaker do. So I'd found some software which was great. So there's this software called 3D Slicer. 3D Slicer is free, and it's on the net, and it's designed for people to use however they wish, although there is a disclaimer that it shouldn't be used clinically, whatever that means. But it's available for anyone to download from slicer.org. So it's a software platform for doing anything with medical images. It's open source. You can use it on Linux if you're really techie. You can use it on a Mac if you're sad. Or you can use it if you're Windows-based like everybody else. It's immensely powerful. In fact, it is too powerful. It has 1 million plugins. You can do things with MRI, ultrasound, and CT scans, which actually is part of the problem in using it. But you can do it and connect it to machines, and it's got a worldwide user base. So what do you do with it? Well, first of all, the best way is you get your patient, and they go to their X-ray department and say, can I have a CD of my scan? And on that CD will be a folder labeled images, or DICOM, which will have several hundred DICOMs, and you import them into your laptop somewhere where you can find them again. You open up Slicer, you make what's called a volume model, so it's a 3D representation. You shrink it down so the amount of data you're dealing with is not overwhelming, so you select a region of interest. And then if you're dealing with bones, you can select a single bone that you want to export as a model. You click Make Model, and then you save it as an STL file. And I'll show you how I do this. So, for those of you who really want to know how to do this, this is a very useful web address for you to photograph. There was an American resident in facial-maxillary surgery who talks you through how to do the bit on Slicer from DICOM files through to an STL output of a model. And that's what I use, and I watched it many, many, many times till I memorized all the steps. But once you've done it and you memorize it, it's quite simple and actually straightforward. Another bit of software that's quite useful is Mesh Mixer, which is made by Autodesk, which is also free, open source. And I use that for trimming the model virtually. And sometimes if it's a big bit you want to print, it's sometimes easier to print it in 2 halves and then get a bit of glue and stick the 2 halves together after you printed it. Finally, you do need some software to make your G-code. If you've got an Ultimaker, you can use their software, which is Cura, which actually, again, is open source and can be used with many different printers. And that makes a G-code file, which you can send to your printer either on an SD card or on a USB stick. It's very configurable, and in some ways it's a bit too complex. So if the gentleman at the back could click my video, I'll run you through what I actually do. So first thing is you open up Slicer, and this gives you a view, and you have to find the files on your CT scans, so you import them, which takes a little bit of time, depending on the speed of your laptop. And then you end up with a patient examination, and you choose the one that looks like it's got the best lot of images in, and you import that in so that you can see what you normally see on a monitor, on a PACS monitor. So you've got AP lateral and sagittal. Then you want to make it into a volume, so you click on volume rendering, and you say I've got a CT scan, and you want to display a region of interest. Centralize your volume, and now you need to shrink down the whole field using the slidey bits to make a small ROI, region of interest. So you can either do it on the virtual model on the top bit, or you can do it on the views below. And you end up shrinking it down so you get rid of all the extraneous information. And here, this is an elbow. I'm trying to get down to the radial head. So I've shrunk it down, and I have a very small bit, and it includes everything. You check all the bits. You can enlarge it. You can change the contrast. And then you go to crop, and you say, I'm going to crop this down and exclude all the other stuff. And here we only have views of the radial head in 3 different views. Now I want to make sure that I only have bone, so you have a threshold limiter, and you slide that so only the bone is flashing, and then apply. And now I only want the radial head, so I'm going to click on the radial head, and then bingo, I've excluded all the other bone. And finally, this is speeded up. I don't type this fast. Finally, you want to make a model, and you save as an STL somewhere you can find it. Make model, and the top picture goes. And now you need to open Mesh Mixer to have a little look. This is just to explain what you can do with Mesh Mixer. So here we've got a radial head, which actually doesn't need anything doing it because I managed to exclude it. These are just showing the shortcuts. But the Mesh Mixer is quite nice for moving it around and chopping it up. Here I've got an elbow that includes all the bits I don't want, so you can just lasso them, chop them away, till you end up with just what I had before, in fact, which is the radial head. I'll just speed this up now. So now I have the radial head ready to print. Click Save. Just get rid of the last little bit. And now I have to open up Cura, which is a slightly older version with the 2+ printer, and import my radial head. And there it is, life-size in the virtual printer. It's quite nice to make sure it's printed vertically to minimize the amount of support you have. So just fiddle around with the rotational settings. I don't really need to see the intact bone at the bottom, so it's quite nice just to sync the model into the print bed. Saves on time, saves on printing. And actually I have to move it off center, because if you always leave it in the center, the middle of your print bed gets worn out. So it's quite good to move it around. Here it's slicing, says it's going to take 1 hour and 9 minutes to print. Make it into G-code, and off we go. So this is an example of an elbow. Just show you, because people always ask, what does it cost? Well, an elbow is quite a big thing if you're printing all of this, and it's 39 grams of filament, but it's still only £1.77, which is quite a lot less than the commercial alternatives. But it's going to take you 9 hours to print this, so get it going in early evening, and it'll be ready when you get up in the morning. So 3D printers, I don't really need to tell you this. There's a lot of them outside, actually. The Ultimaker 2+ costs just under £2,000, and the 3, which is the one with dual filament, which has its advantages, is just over £3,000 by the time you include VAT. You've seen them outside. They're about 13 inches square, and you can make things that are quite big if you've got the time. But it's very high quality resolution, and you're limited by your CT scan and not by the printer. So this is a 2+, and you can see the filament on the back going over the top into the hot print head and squirting out with the build plates. And this is an Ultimaker 3, and the only thing to note is it's got 2 lots of filaments going in, which has some advantages if you want to print with 2 materials. I would recommend, and I would plug, and I've had to pay for this, so I'm not getting any money, build Tack mats and their flex plate. When you have a 3D printer, there's lots of magic to do with blue tape, hairspray, glue. I found that if you just stick a build Tack mat on the build plate, everything sticks. Then you find it sticks so well you can't get it off, so you then need to invest in a flexible magnetic plate. So once you've got your print made and it's stuck to the plate, you wiggle the plate and it pops off without any pain. This made a huge difference to the success of my prints. So quite expensive, but worth every penny. I print in PLA for bones, and I like white because it looks like a bone. It's rock hard, you can drill it, you can cut it. You can print in other materials, but it's completely unnecessary. And PLA is the cheapest. It's made from cornstarch, so the smell when it's hot is quite pleasant. And that's just a print of a metacarpal surrounded by the raft on a build Tack plate. So can we just run the video? So this is, you can see it outside. Printers take an awful long time to build it up layer by layer by layer. So I'm not going to stand here for 9 hours while this prints. Can we run this video? So this is what happens when you print an elbow. It builds up. Can we run it again? The same thing. Yeah, so there's supports on either side, which supports the overhanging bits, and then it takes 6 hours. Not much support and quite cheap, but the bits can be prized apart and you can reconstitute the bone. So the lessons I've learnt in doing all of this is that it's usually better to print end on than flat. You get a better quality print. As I said before, you can split a big bone and glue it back together using Cura. I had a lot of problems in the beginning with bones because they're very complex on the inside, and if the filament retracts a lot, it can block the print head. So I set the Cura to have the minimal number of retractions. As I said, a build tap mat and flex plate makes a huge difference and makes it much more reliable. Also increasing the temperature seemed to help a bit. And don't always print on the same bit of your build mat, otherwise it'll wear out. So why am I doing this? I'm a clinician, not a mechanic. I'm not an expert in 3D printing. So I needed, or I wanted to have the models in my hand for clinical use. So if you've got two of something and one is broken, you can make a model of the uninjured side, mirror it, and then see what the broken side ought to look like, which is quite useful if you're doing corrective surgery, say of a clavicle. You can use it to see if the implant you're thinking of putting in will hold the bone in the position and all the screws will go in. You can plan the way you're getting to the bone. So I have changed my incision that I was about to make just before I did the operation, having gazed at the model for some hours. It's quite useful for consenting the patients. You can show them their fracture and try to explain what you plan to do. And some patients want the model to take home as a memento. So for those of the uninitiated, this is a side view of a metacarpal, which is one of the long bones in the palm of your hand, which is not meant to be bent. It's been fractured in the past, and so I planned how to straighten it, and in particular how much bone to take away to end up with a straight bone that would take a plate. Scaphoid, another funny bone, probably half of you, 3/4, 90% never heard of, but it's a little bone in your wrist that often breaks and doesn't heal, and quite difficult to get a screw all the way down the bone, and it's not very big. The bone itself is 2 centimeters, so in order to help understand what was going on, I printed it double size and made it 4 centimeters, and I could work out how to fix the fracture and graft it. This is your shin bone, distal end, which is quite a complex fracture in 3 different planes, and there are various different plates you can put on, so it was quite nice to be able to think, well, if I put the plate on the side, it's not going to help the front, so I need a plate that goes around the side and the front. This is side, it's on its side, but it's actually your upper humerus, printed on its side. But it's that way up, the ball is come off the shaft, so there is a plate that you can apply that holds it back in place, and you can plan how that plate's going to hold the fracture. This is quite interesting. It's quite an unusual fracture to fracture your shoulder blade. It's quite a big bone, but actually to understand the fracture, to comprehend it, you don't need to print it full size. So I actually printed it 1/3, and then we fixed the fracture. Having understood where the fracture line was and where the plates would go. This is a really unusual fracture. This is the side of the elbow, quite an unusual, and there's a little flake of bone which I've actually put back in place with a bit of blue tack. So I printed it, levered the fracture bit off, put some blue tack on and put it back where it belongs. And then I needed to know there's a very specific plate that either works brilliantly or is a complete waste of time. And so I went to the operating theatres, opened up the sterile kit, got the plate out, and I could see that this plate would actually do what I wanted. So I did the operation, and I'm sure it saved me an awful lot of time during the operation to be able to know this beforehand. As I said, PLA is hard enough to drill, so you can plan where you're going to put your wires. So the cynics would say, do you need it? Well, you don't need it. You can, everyone else is managing without it. Can we just run this video? So this is a, oh, hang on, can we go back one? Okay, can we run this video? So this is a shoulder joint, so there's a socket with the ball taken away, and there is a relatively simple fracture. You don't need a bone model to help you understand this, although it is quite nice to hold it in your hand. It's kind of luxury. Can we run this video? So this is another shoulder fracture, but even the orthopaedic surgeons in the audience will say, what is going on here? And I think that's a very good question, because you really find it quite difficult to understand what's happened to the socket in relation to the rest of the scapula. So in this case, even a virtual 3D model doesn't tell you what's going on and where the fracture is. And so what I did is I printed it and then took all the bits apart. It doesn't show very well on this, it's all white. But I took all the bits apart and then I put Humpty Dumpty back together again with the help of some blue tack. Unfortunately, I couldn't use blue tack during the surgery, but the principle's the same. So it helped your understanding of what's going on in a very difficult fracture. Rotational abnormality in the long bone is quite difficult to visualize with a CT scan or any other image. Those of you who are awake and understand these things, the bottom end of this model shows a front-to-back view of the ankle. The top end shows an almost side view of the knee. On the x-rays, it looked great. The only trouble is that this lady's foot was pointing out 60 degrees sideways because the fracture had been fixed rotationally in the wrong position, and we needed to see how much and why. It wasn't me who did her operation, I hasten to add. The interesting thing is she has a plate on, and with the CT scan, the plate came out quite nicely on the model. And you can see the screws going through the bone, and you can see the plates and the screw heads. I have learnt that I don't think pink's the best color to print it in. This is another hand fracture. He had a fracture of the most left hand of the long bones at the base, so the 5th metacarpal. And I was planning to fix it in a particular way that fixed the 5th to the adjacent one with the 4th, because it's minimally invasively, if you like. One can see on the side view on the right-hand picture, there's some fracture fragmentation of the bone nearest to you. Well, what became apparent when I looked at this model is what I hadn't appreciated on the CT scan is just beyond the bone nearest you, you can see a fracture line in the next bone. So actually, fixing the 5th to the 4th would have been the wrong thing to do, because the 4th was also broken, although undisplaced. So what do I think about 3D printing? I think I like to spread the word. I have no financial gain to do this. I've put my videos on the internet. I really want, as the previous speaker said, I want everyone to learn about it and make use of it. It is useful for elective reconstructive surgery in fracture management, as in malunions, but I think it's very useful in acute fracture management in any bone. I mean, I've listed some of the ones I've done, but really any long bone can be modeled. And it is good to show the patient. They are impressed that you've taken the time to model, and you can try and explain to them what you're going to do, so it helps with informed consent. I think it is now affordable. I mean, a couple of grand for a printer, for an orthopaedic department, even in the stretched NHS, is something that they could afford, because the software is free. The only problem is it's not quite plug and play, so the department needs a person or more than one who is an enthusiast who will just spend the time learning the steps on how to use the software and how to use the printer. What next for me? Well, I've got this sussed, I think. I'm just spreading the word. I am trying to now scan hands on the outside to see if I can make models of hands prior to surgery. and in my spare time, I'm using a 3D printer to print bits for boats. Thank you very much.